Okay, yeah, hello everyone, and yeah, thank you very much for joining us today, and welcome to the first joint EurJOC ChemPhotoChem Virtual Symposium on Photoredox Catalysis. My name is Nijs, I'm the editor of EurJOC, and it's my pleasure to host this meeting today on behalf of both journals, EurJOC and ChemPhotoChem, and also Chemistry Europe, our society publishing partner.
And my name is Deanne Nolan. I am Deputy Editor at ChemPhotoChem, and from my side, I would also like to thank you all for joining us here today for this event.
So Deanne and I will guide you through the symposium today, introducing the speakers, and we're very happy that Burkhard König is today with us. He's the chair of EurJOC, and I think the perfect moderator for this event on Photoredox Catalysis. We have a fantastic lineup of speakers, and we have Timothy Noël from the University of Amsterdam, Jola Pospech from the LICAT in Rostock, and Tehshik Yoon from the University of Wisconsin-Madison. And they will all cover different aspects of photoredox catalysis in their talks. Each talk will be followed by a short Q&A, and this is moderated by Burkhard. And to participate in the scientific discussion, please put in your questions in the question function field. I'm happy to say that this is not the first time that EurJOC and ChemPhotoChem have joined on an initiative together. We have actually published a special collection on photochemical synthesis 2 years ago, and Burkhard and also Tehshik were among the guest editors of this special collection. And now, I would like to hand over quickly to Burkhard to say a few words and set the stage for the meeting.
Yeah, Anna, thank you very much. It's my great pleasure to be part this afternoon of this symposium. The photocatalysis indeed has developed into a very vibrant field over the last 2 decades, and it's fantastic. We have people here like Tehshik, who was there really at the beginning, and Timothy, who really made great contributions to it to larger scale and practical, and giving new aspects on the ongoing photocatalysis. So that's really amazing. I think it's a field that still has a lot to offer, and I think it's a perfect format to kind of discuss a little the new trend over in this symposium. I look forward to the 3 presentations.
Okay, then maybe we can begin the scientific program. So first of all, our first speaker today is Timothy Noël from the University of Amsterdam. So just to give you a brief biography, he received his MSc degree in Industrial Chemical Engineering in 2004, his PhD in 2009 at Ghent University in the group of Professor Johan van der. Next, he moved to MIT as a Fulbright postdoctoral fellow with Stephen Buchwald, where he worked on the development of new continuous flow methods for cross-coupling chemistry. In 2012, he became an assistant professor at the Eindhoven University of Technology, and in 2017 became associate professor at the same institution. In 2020, he was promoted to full professor at the University of Amsterdam, where he is the chair of flow chemistry. Timothy has received several awards, most recently the prestigious 2021 KNCV Gold Medal from the Royal Netherlands Chemical Society. His research interests are flow chemistry, homogeneous catalysis, and organic synthesis. And today we'll talk to us about innovation in photocatalysis through the use of flow. And I see you've already shared your screen, so thank you very much, and we look forward to your presentation.
Okay, thank you for the kind introduction, and also to invite me for this very interesting symposium. I'm very happy and honored to be able to speak about our research in front of you all. Do you all see my slides well?
Very good, visible.
Yeah.
Okay, perfect. So without much further ado, I would like to speak a little bit more about our research into flow chemistry, and specifically on the innovations that it can provide in photocatalysis. And before I dive into the topic itself, I would like to give one slide about what we are typically working on. So what we tend to do is that you have a given chemical space which is available for synthetic chemists, and what we are really trying to do in our field is like expanding the available chemical space by using technology. And one of the things that we do is develop new synthetic transformations which utilize reagents or reaction conditions that are a little bit challenging to handle. I will give you a couple of examples in this talk today. We also try to develop new tools to make synthesis easier, also with the focus on scale up, for example. And by using these, like for example, flow reactors, we really try to push the field of synthetic organic chemistry and try to show unique and reactivity modes and selectivity modes. And we do that essentially by merging organic synthetic chemistry with chemical engineering. We really believe that these two are not only amplifying each other, but also shaping the way you do synthetic chemistry and shaping the reactors that you design for these type of disciplines. Now, one of the reviews that I like to show you today is this one from 1926. This is only the third volume of chemical reviews, which is now a very established journal for publishing review articles. And normally when I write a review, I would say, okay, we start nice and how fantastic our field is, and then in the outlook we say, okay, what is still needs to be fixed. These guys, they essentially at the third sentence already, they are saying that photochemistry is in a very unsatisfactory state. And so the question that we have to ask ourselves is like, why are these people saying that from the get-go? And so one issue that you could think about is how are we going to activate organic molecules? And if you want to activate an organic molecules, the way to do that with photons is that it actually has to be able to absorb it and get into an excited state. But most organic molecules cannot easily absorb light unless it's of a high energy content like UVB and UVC type of irradiation, which gives you a lot of energy, 603.50 kJ per mole. And that's of course fine if you're working with small molecules, but if you're working with, for example, pharmaceuticals or agrochemicals, which have a lot of different functional groups around its core, then it can be that not only your reaction is going forward, but also a lot of byproducts are generated because of the high energy. So essentially you're destroying your molecule. Now, one of the issues with UVB and UVC irradiation is also that not only there is not sufficient amounts of that in the solar spectrum, but also your light sources tend to be more expensive and less high intensity. And the high intensity is an important thing to remember because that's also important for when you want to scale these type of chemical reactions. Now, the key thing to use is to use photocatalysis, where you take advantage of transition metal complexes or like organic dyes, which can absorb visible light. And once you absorb that visible light, you can get into an excited state, and then you can start doing redox type of chemistry. This is well known to most of us now. I mean, in the last 2 decades, we've seen really an uptake of this type of activation modes. And recently, Paulo Melchiori, he was a guest editor of this special issue, Photochemical Catalytic Processes, and a lot of new reviews are being shown now on the ASAP section of chemical reviews. So it's definitely something worth looking at. Now, the advantage of using visible light instead of other lights, which are more energetic, is that you can also use cheaper and lower energy light sources. So energy light sources that are a little bit easier and favorable for working with molecules. And you can also buy them in high intensity, these LEDs. This is important for the activation of those molecules. So just to compare, if we have a thermochemical activation, like a thermal way of activating molecules, we tend to use the Arrhenius equation, which dictates that your reaction rate is dependent on your reaction temperature. So the higher the temperature, the faster your reaction often will be. Now with photochemical activation, something different is going on. So here your reaction rate is critically dependent on the intensity of the photons. So the more photons you have, the faster your reaction rate will go. And so if we plot this equation into this schematic, you will see that in the x-axis we have the photon flux density, and here we have the reaction rate in the y-axis. Now, when there is no light shine onto your reaction mixture, essentially you will have no reaction. So this is also interesting in terms of safety. When your reaction is going out of control, you just remove the light source and you're already quite fine to go forward. Now, the more photons you shine onto this reaction mixture, the faster your reaction will go, until at a certain moment that your entire reaction mixture is saturated with photons. And at that point, a further increase in photon density will not deliver a better outcome. And so essentially here, a lot of energy is wasted. If you want to expand this or extend this linear regime, the way to do that is maybe to add more photocatalysts or other photon absorbing species in your reaction mixture. And this is important for the next part of my talk about scale up. Now, this is definitely one of the issues, and the main culprit for that was the Lambor Beer Law, which dictates that when you shine light through a reaction mixture and you have highly absorbing species like photocatalysts, like ruthenium bipyridine, for example, what you will see is that these molecules are very good in absorbing photons, but that also means that while you're traveling through your reaction mixture, the intensity is going down quite rapidly. And so even in a matter of a few millimeters, you essentially have no photons anymore to your availability. That means that the highest reaction rates are observed. Remember that rate law that I showed you a few slides ago. The highest reaction rates are going to be observed at the reactor wall, while in the center of your reactor, essentially your reaction rate is 0. So this also means that if you're doing photocatalysis in a small flask, it's going to go pretty well. You will have your complete conversion in maybe less than a day. But if you're going to scale this up in a classical way, like for example, you're going to take a liter flask, your reaction times will go up exponentially. And so this is going to be, the culprit is here then the Lambor Beer Law. So we need to, if we want to scale this type of chemistry, we have to do other technologies to do that. Now, the way to do that is to use microreactors. So reactors which have small dimensions, for example, capillaries, which are transparent. So these are PFA capillaries, quite cheap. We buy them about €1 per meter. And so we coil that, and around it, we shine light on it. And so then you have a very good irradiation and a uniform irradiation of your entire reaction mixture. And essentially, all the molecules within that reaction mixture will perceive more or less the same light intensity. So because then your reaction rate is also high everywhere in that reactor, we will also see that we can reduce the reaction times. Typically, a few minutes is already sufficient in most cases. And because of that, you can remove the product faster from the irradiated zones, and that will give you less byproducts. Now, how are we going to scale this further? So one microreactor can be sufficient to get enough, like grams per hour or even per minute. So how are we going to reach now the production scales that is needed in the industry? So for that, you could have this very simple formula, which is the formula of a cylinder. And so there are 3 different parameters here. So the N is the amount of reactors that you would put in parallel. We call that numbering up. And so the more reactors you put in parallel, the more you can start producing. You can also increase the length, which is then just a larger volume. And if you then keep the residence time the same, that means that your throughput overall will be faster. So more will be coming out of that fine tube in the end. The last part, and this is the most powerful one because it's to the power 2, is the diameter. So if you have a little bit larger cross section, there also this will work. And so in theory, what we will have to do is, when we bring this from lab to production scale, is to make have these all 3 working in cohesion. So not one of them will be the final solution. I think actually all 3 will be important. I will give you 2 examples. One is this capillary microreactor that we've developed in collaboration with our friends from Signify, which is the former Philips lighting branch. And so what we do here is we use super powerful LEDs. So this is a 365 nanometer reaction with decatungstate. I will show you a little bit more about this chemistry in a moment. And so what you need to do is, so you have here these very powerful chip on board LEDs, 24 watts optical power. So to keep them at room temperature, you need to cool them with a ventilator. And so we have 6 around this capillary microreactor, which is here. And so then in total you have 144 watts of optical power. Now, because this is a huge amount of photons, that means also that you can reduce your resonance time and a little bit higher catalyst loading. And with that, we can push this, essentially blast it through the reactor. And in that way, with a small reactor, even 11 milliliter of volume and 750 micrometers inner diameter, we can still produce more than 2 kilograms per day. That's in principle sufficient to sustain clinical trials within a pharmaceutical company. So you can imagine if you want more, you can have a couple of these small reactors. They are not bigger than this size, like a little bit more than a soccer ball. And if you have a couple of those, you are in principle able to produce quite large quantities of these compounds. Now, if you want to do more complicated reaction conditions, you can think about multi-phase reaction conditions, think about gas-liquid reactions, liquid-liquid reactions. Then the interfacial area between the two phases is going to be very important. This for mass transfer reasons I will show you in a minute. Now, we developed together with my friends from TU Eindhoven, John van der Schaaf, his group, this spinning disk type of reactor. So essentially, it's a spinning rotating disk that is rapidly spinning in a small box, and the distance between the box and the spinning disk is kept as small as possible, like 1 millimeter to 2 millimeter. Because of that, you have very high shear forces onto your reaction mixture, and that will make these small, that will disperse essentially one phase into the other and provide you with the higher mass transfer rates. So this is a picture of the setup. You have here your pump, your engine, which rotates the spinning disk, and here you have the supply of the reaction mixture, and here you have the exit then. And so in that way, you can here then expose it to light, which is coming from the top. The reaction that we did was a 4+2 cycle addition with singlet oxygen to generate ascaridol. And the reason why this worked so well is actually shown quite well with these GIFs. So at low RPM, so 500 RPM, what you see is that the gas is going to aggregate towards the center. So your interfacial area between the gas and the liquid phase is not great. So you can imagine that also the diffusion of the gas into the liquid phase is not going to be fantastic. But the higher the RPM, the more fine the gas bubbles are. And the finer the gas bubbles are, the better the interfacial area, and so the better also that your reaction rates will be for the diffusion of the gas into the liquid, and in that way you also have better selectivities. Now with that, I also would like to show you a little bit of synthetic methodology and how we think it actually made an impact into like by flow. So one of the things that we have been working on in the past 3 or 4 years is hydrogen atom transfer photocatalysis, where we try to activate CH bonds in alkane fragments, which are very interesting moieties, and essentially every organic molecule has them. And so if we can activate those selectively, then we have a powerful handle to do chemistry. And so we were attracted by decatungstate photocatalysis. I saw once a lecture from the people from Pavia, and they showed this catalyst, and essentially this is a catalyst which is activated by UVA light sources. You could say, okay, now you're talking about UVA. Well, essentially UVA light sources are not that big of a deal. They are the same technology as blue LEDs, and so you can also get them in very high power versions. So essentially UVA is not that big of a deal when you're talking about UV photochemistry. Once you get into an excited state, you can do a hydrogen atom transfer, which essentially means that you can pull off one of these hydrogen atoms, generate an alkyl radical, which is nucleophilic in nature, and then you can treat it with whatever moiety, and then you can functionalize these alkanes. Now, the beauty of decatungstate photocatalysis is that you can tune not only with the electronic properties of the molecule, so polarity match and mismatch effects with your decatungstate photocatalyst, but you can also play with the bulkiness of this molecule and the concomitant substrate. So if you think about small molecule HAT, like chlorine radicals or other type of small molecules, then you will see that it's very difficult to discriminate between these different secondary CH positions. While with decatungstate, because of the bulkiness of the molecule, you can selectively go for the least sterically hindered one. And this allows you to actually exploit this reactivity in quite complex organic molecules. One of the first examples that we've done was the use of oxygen and combine this with that as an oxidant to install carbonyl groups onto aliphatic moieties, as you can see here. So what we do is we take a pure oxygen gas, we dose that into the liquid stream with a mass flow controller. Once it's merging with the liquid stream where all the hydrocarbons are in there, you can get this segmented flow regime where you have an intimate contact between the two, the gas bubble, which is the reagent or like the one of the reagents, and then the substrate, which is dissolved into the liquid phase. And as you can see here, the blue is where the liquid is, and the white is essentially where the gas bubble is. And so the intimate contact between these two makes sure that this reaction goes pretty well. So you can do a whole variety of molecules, also small molecules, but also a little bit more complex drug-like molecules. And also, as you can see here, we can do artemisinin in a very good regio selectivity and quite excellent isolated yield on a 5 millimole scale. Now, these are liquid and solid state alkanes, but we wondered also if we could activate CH bonds in gaseous alkanes. They are one of the most difficult to cleave CH bonds that we know of, and especially methane is very, very challenging. So any process that is that is known into the literature, like for example Fischer-Tropsch type of chemistry or oxidative coupling of methane, these are all processes where you need to use temperatures around 500 degrees C just to get those radicals to be formed. Now, if you want to do that with organic molecules and engage that with pharmaceutically relevant molecules, you need to lower the temperature at least. And so with decatungstate photocatalysis, we can do now this type of chemistry at room temperature, and we can engage them into useful types of chemistries, as you can see here. These are all isolated yields, and there are more examples in this paper. And the key here was really to use flow, because if you want to do this, and we need sometimes higher pressures, 10 to 45 bar, then you need power apparatus, which is equipped then with a window to supply the photons. While in flow, the only thing that you need to do is pump it at the right pressure through the reactor, and then you can bring it onto the level that is needed here. We can also do CC bond formation, where we merge it with a nickel catalytic cycle. And so here we do acylation type of chemistry, also for very complex moieties, as you can see here. So here the two different catalytic cycles are playing and are intermingling with each other. We also wondered if we could install allyl moieties, and this is some recent work that we just put out on ChemArchive, where essentially we generate via decatungstate photocatalysis a alkyl radical, which then can attack onto this Michael acceptor, and this intermediate is formed after 5 minutes in the flow reactor. Now, if we immediately merge this with a suitable aldehyde, we can do in the second reactor a Horner-Wadsworth-Emmons without intermediate purification. And in that way, in one single flow scheme, we can start producing all these different molecules, and depending on the aldehyde, you can tune the double bond that you're forming. So essentially, when you work with paraformaldehyde, you have these allyl moieties that you're installing onto these hydroalkanes, or if you're doing a deuterated paraformaldehyde, then you can install these deuterated bonds here. Very interestingly, also, I think in terms of for mass spec within the pharmaceutical industry, or you can dial in these other aldehydes, even alkyl ones, to generate these very complex double bonds, as we show here, in a very simple way, all done in flow. One of the things that is an issue with hydrogen atom transfer photocatalysis is that you generate these nucleophilic radicals. So essentially, if you want to quench this with nucleophiles, this is going to be a little bit more challenging. So the trick is to do a radical polar crossover, for example, to oxidize it with TBHP, and then you generate this positively charged carbon here, and then you can start merging it with nucleophilic partners like these azoles, for example. Then you have a whole variety of molecules that you can start engaging now with decatungstate photocatalysis or hydrogen atom transfer photocatalysis. And then finally, you can also use these type of Michael acceptors. If you have an inactivated hydrocarbon, you are going to expose it to the photochemical conditions. You generate a radical, you let it attack to this double bond, so these diazo dicarboxylates, and then you generate these protected hydroxides. When you then dial in these type of molecules, you can again, without intermediate purification, do a Knorr type of pyrosolation, generate pyrosols, or even make, if you use these type of moieties, to make these corresponding phthalazinones. So again, building up complexity without too much of a hassle, all in one continuous flow stream. So you can really engage two type of reactivities and immediately use these type of molecules that you're generating via the photocatalytic process and immediately engage them in a follow-up reaction without intermediate purification. Now, I hope I showed you that microreactors can be useful for photocatalysis, and essentially it's also useful for other types of activation modes. Think about electrochemistry that we are also working on in the group. And as Anne already said, I also was a postdoc in the Baco group, where we also did some cross-coupling, classical cross-coupling chemistry in continuous flow reactors. So there are many, many advantages, and I would, if you are not familiar with flow chemistry, and there are quite a number of very good reviews, so I would say start with that, reading those a little bit. And if you are then convinced that also your chemistry can be benefiting, then I would say let's do it. Just give it a shot, and really look at the advantages of flow, and then do those reactions that you think it's worth pursuing, because then you will see benefits in your own chemistry, and of course that will give you the best results in the end. So I would say give it a shot, and if you have any problems, you can also be in touch with us later on. I would like to thank my team who are doing all the work. I'm very grateful to be able to work with these people, both past members as current members, and they are extremely hardworking people and very energetic, very interested in this type of chemistry, and so they are all doing flow chemistry. Not always trained engineers, so we have a mix of engineers and chemists, but it doesn't mean that if you have a pure classical chemistry education, it's still possible to really get better into flow and actually appreciate the benefits of it. I also would like to thank our sponsors, because without those sponsors, we cannot do too much. So I'm very grateful for the confidence that they have in our research lines, and I hope they will keep sponsoring us in the future as well. With that, I'm at the end of my talk, and if you have any other questions, feel free to ask them. I would be very happy to answer them.
Yeah, Tim, thank you very much for this very nice overview. I think you kind of are convinced, hopefully, a lot of our audience to give it a try with flow. And the first questions came in. If you have questions in the this goes to our audience, please use the question part here. Just write your question in there. I see them and select the ones we can address to Tim. The first question that came in was addressing your spinning disk reactor, because you've shown this liquid air. Can you also do liquid solid with this setup?
Yeah, there was actually not liquid air. It was just gaseous air that we used, or gaseous oxygen. And then the question of the solids, yes, we can. Actually, we are now working on a manuscript where we show that because of the mechanical energy of that spinning disk, it doesn't clog anymore, which is one of the Achilles heels of continuous flow reactors. While in this spinning disk, because of the mechanical energy, the clogging cannot occur anymore. So you can handle slurries of semiconductor photocatalysts very well.
Oh, right. That's interesting. Another question that came in was regarding the decatungstate catalyst. And I would be interested also to hear your answer. How can we kind of tune the photocatalytic properties of the decatungstate to make it even kind of better? Have you thought about this, or any activities in this direction? Or you leave this to others?
We haven't done that, but I've seen that people sometimes use the counter ion. So we use the turbidyl ammonium ion, but in principle, you can also tune it a little bit there. And I think the Britain group once exploited that effect for directing the catalyst into certain regions within a molecule. So if you have an amine within your molecule, that you can bring it closer. And actually, they saw accelerated rates for those type of reagents that had actually an amine inside their molecule. That's one opportunity. But for the rest, I need to actually, I'm not so sure. So I know that people are working on it, but I'm not the specialist in this. So some people are trying to push it into the visible light region, for example. But so far, this is the best catalyst.
Yeah, there's another question that is more specific. And can we use your technology for wet photoreforming to produce hydrogen using flow microreactors? Has this been applied?
Yeah, I haven't done it, but I would be surprised if not. So I assume, because the advantage of these plug flow reactors is that it can handle gaseous reagents quite straightforwardly in comparison to classical batch type of vessels. So I would assume that it should work, and that you immediately can also evacuate, and maybe even with membranes in the next step to evacuate the hydrogen in that way. So
right.
I don't see any reasons why not.
Okay, right. So parts of the audience really looked in detail at the conditions you showed us on there, and they noticed why are you using HCl when you use the decatungstate as a catalyst?
Yeah, so in this specific slide, so that was one of our earlier work. There we saw that so one of the things is when you want to polymerization of decatungstate is that it occurs in acidic medium. So essentially the catalyst also works a little bit better if it's slightly acidic. If you have too much base, for example, then you get a little bit depolymerization of that polyoxomethylate. Now, having said that, with this specific, I don't have actually the example here, but in the paper there's one example where you get over-oxidation. So if you then remove the acid, which it makes the catalyst a little bit less active, then you can actually steer the selectivity to the oxidized species that you wanted and don't have over-oxidation. So it is important, but it's on a case-by-case scenario that I would try it and either leave it out, depending on how reactive your system is.
Right. Okay. Two more technical questions, and I combine them. Viscosity, is this a concern of the reaction medium? And the second one, the decatungstate, can you also immobilize this? Because you have it in a slurry, can you, or in solution, can you immobilize it to make it heterogeneous?
So maybe the viscosity issue. Viscosity can be an issue because you're pumping stuff through a narrow capillary. So then your pump needs to work a little bit harder. Essentially, the spinning disc can handle that as well. So not too much of an issue there. But of course, every time you have a higher viscous solvent or whatever, then your pump just needs to work a little bit higher. So it's a little bit depending on which case. Now, with regard to the immobilization of decatungstate, I've seen some examples in the literature where you again can exploit these counterion, and if you would fluorinate it, you could essentially integrate it into a fluorinated membrane. We are also looking into size exclusion, nanofiltration, where we try to recycle the homogeneous catalyst, and in that way we can keep the advantages of working in homogeneous, but still be able to recycle the catalyst. And actually, I hope that early next year we will be able to publish this work.
We have to kind of move on. One last question with a short answer. When you increase the power of the light source, things get hot. How well do you control the temperature in your setups? Because some of the light sources were super powerful you were using.
Yeah. Well, essentially, we put a ventilator here on the reactor compartment, as you can see here. Now, having said that, very shortly, in principle, we stopped at 24 watts here. You can have higher watts, so 48 watts, these chip-on boards can go, but then you need water cooling. So definitely your energy balance with regard to higher temperatures, you need to take that into control, because your LEDs will work less efficient when they are at higher temperature, and even it might wavelength shift a bit. So you have to take that into consideration.
Right. There are more questions coming in, but Tim, we have to move on. I would like to ask you to go into the question section and answer them just by writing while we move on. Thank you again for the brilliant talk.
Thank you.
Discussion. I hand over to Anne to introduce our next speaker.
Okay. Thank you very much. And yeah, thanks, Tim. This was really fantastic. And as Burkhard said, you can also see that the audience enjoyed it a lot. A lot of questions came in, and there's much interest in getting to know more about your chemistry. And I would now like to move on to the second speaker, which is Jola Pospech. And so Jola received her Bachelor and Master of Science at the University of Göttingen, and here under the supervision of Professor Lutz Ackermann. She then moved to the Leibniz Institute for Catalysis, so the LICAT in Rostock for her for her doctoral studies, where she completed her PhD in 2015 under the supervision of Matthias Beller. She then moved to the University of Illinois as a DFG postdoctoral research fellow in the group of Professor David Sana. She then came back to Germany to the LICAT, and she has been an independent research group leader since November 2016. Her research interests include the development of organocatalytic oxy-functionalizations of aromatic and aliphatic compounds through photo-induced atomic oxygen transfer. So Jola, thank you very much for joining us today, and we look forward to your talk.
Okay, thank you very much, Anna, for the kind introduction, and of course, thank you for the organizers for inviting me. Also, it's especially exciting these days to talk about our research in front of such a big audience. So in the next couple of minutes, I will talk about the development and application of Pyrimidopteridine Photoredox Catalyst, which we kind of serendipitously discovered. So I will introduce you to the synthesis and characterization of these organic photoredox catalysts, which have really really excellent excited state reduction potentials and are suitable to oxidize most organic molecules. We also found out that the pyrimidopteridine N oxides can be considered as pre-catalysts and can be activated due to photo-induced oxygen atom transfer, and also the plain heteroarene is an excellent organic photoredox catalyst. We applied this catalyst in 2 reactions which are published so far, many more to come. One is the decarboxylative CC bond formation, and the other one is the photomediated hydroamination of primary amines, of stilbenes with primary amines. So how did we come across these peculiar heterocycles? So as Anna told you, we are interested in finding mimics for monooxygenase enzymes to do an aliphatic on aromatic oxidation reaction. And if we look at the enzymes which are capable of doing this in the body, we of course come across the famous flavine-containing monooxygenases enzymes who can either oxidize organic molecules through this prominent flavine C4A peroxide species, but within the last couple of years, also this flavine 5N oxide species was identified as potent oxygen atom transfer species. So we ask ourselves whether we can take pyridine N oxides and activate them with visible light or electrochemically to transfer the oxygen atom to aliphatic or aromatic compounds. And first of all, we carefully reviewed the literature, wrote this review, which is about the topic where we identified pyridine N oxides that are used as oxygenation reagents. And there is one very prominent example here. This is a pyrimidopteridine N oxide, which was known as stoichiometric oxygen atom transfer reagents that can undergo biomimetic reactions. Here is an oxidation of an methyl group alpha to an hetero atom, which produces a CN cission product, or this reagent can be used to oxidize arenes. So this is what we wanted to do, but we wanted to do it in a catalytic fashion. And first of all, we wanted to understand why this oxygen atom transfer happens. So pyrimidopteridine is kind of a tongue twister. This heteroarene consists of a condensed heterocycle between a pyrimido unit and a pyridine unit, and is in the following abbreviated with PPT, or in case of the N oxide with PPTNO. So first of all, we set out to synthesize a bunch of these heteroaromatic N oxides. And the synthesis is really straightforward from inexpensive commodity chemicals using symmetrically or unsymmetrically substituted ureas, and couple them with cyanoacetic acids to form these aminouracils, which can be nitrosylated. And these compounds are obtained in these bright pink powders, and then undergo a radical dimerization reaction to form this pyrimidopteridine N oxides. We optimized the synthesis using a lead-free variant. So here you see in the initial publication by Markey and co-workers, lead tetraacetate was used in stoichiometric amounts, and we switched this with the more environmentally benign PIDA reagent. All compounds are obtained on a gram scale, are highly bench stable, and can be obtained in high crystallinity. And this was also something we found that the arrangement in the solid state is kind of peculiar, because we don't have the pi stacking that is usually seen in aromatic compounds, but we see this stair-like arrangement of two neighboring molecules, which then goes on, so you get a stair-like motif in the solid state. And this is reminiscent of a non-covalent interaction. And we calculated the electrostatic potential map, which is seen here. And you see that we have an area of high electron density in the periphery of the molecule and a pi electron hole in the center of the arenes. And now this regime of high electron density can pack with this pi hole. We were interested in what kind of non-covalent interaction
So we seem to have lost our speaker. We give her a minute to reconnect and see if she can come back. Just stay tuned.
So can anybody hear me?
Yeah, yes, yeah, it seems like you're
Yes,
back.
I'm so sorry, my computer just stopped. So this is a disadvantage of doing presentations online. You can just disappear, right?
Yeah, but if you reappear again, it's good.
Exactly. Yeah.
Presentation is back on there, and now then we need to see you again, and then we can continue.
I think I will just leave the camera off. Maybe it works better this way.
Mhm.
That's fine. Okay, please go ahead then.
Okay, thank you.
Yeah, but unfortunately, my computer froze again. So back again.
Perfect. Please go ahead.
Okay. So what we had to do to figure out if yes, why our heteroarenes are photoactive reagents, or we had to figure out which photophysical and electrochemical properties the pyrimidopteridine N oxides and the deoxygenated heterocycles have. And for this purpose, we had to fill a table which was all blanks, and just a quick overview what we really need to investigate the photochemical properties of compounds. We have to have an appropriate absorption maximum that that the molecule can be excited with an appropriate wavelength. We have to determine the excited state energies and the ground state reduction potentials and redox potentials. And the excited state redox potential is then calculated by this simple formula, which is shown in the footnote. So we applied UV-vis absorption spectroscopy, where we identified the absorption maximum, usually around 370 nanometers. Then measure the record the emission the emission spectra, and the excited state energy is calculated by the intersection of the normalized emission absorption and emission spectra. Furthermore, we need the ground state redox potentials, and if a redox event is a reduction event or oxidation event is reversible, the reduction potential or oxidation potential is easily calculated by the halfway potential of the minima and the maxima of the CV wave, but it becomes increasingly more difficult if we have irreversible redox events. And in this case, you can easily apply DPV measurements. And here, this voltammogram reflects the turning point of the CV curve here, and the maxima equals pretty much the half-wave potential, which is otherwise difficult to calculate in irreversible oxidations. So what we see is that with the alkyl substituted pyrimidopteridines, we have a close to mirror image symmetry of the absorption and the emission spectra. But if we have aromatic substituents attached to the heteroarene, the emission maxima becomes much broader. And we identified this originates from a charge transfer event from the core arene to the phenyl substituents, and this band could be a much more defined emission spectra could be obtained when doing the luminescence measurements in benzene instead of acetonitrile, because it has a much lower permittivity. Because in the flavine photochemistry, the triplet state is a very important excited state. The reviewer, when submitting this paper, asked us whether this is also important. The triplet excited state is also populated in our system. And then we had a really nice collaboration with the physics department led by Stefan Lochbrunner here, which applied transient absorption spectroscopy. And we identified that, for instance, for the tetraprotyl substituted pyrimidopteridine, about 50 half of the excited state molecules are singlet and half of them are in the triplet excited state, whereas with the for the tetraphenyl substitute pyrimidopteridine, a significantly larger portion resides in the triplet excited state. So how do these organic photoredox catalysts compare to other commonly used photoredox catalysts? We see here that the absorption maxima is important. And here, although we are in the UVA region, we are still happy with this. Of course, it's preferable to shift this absorption in the visible region. But as Timothy pointed out, we have good equipment to still excite our compounds in the UVA regions. We have here a very simple setup with 2 UVA panels. We can run 6 reactions in parallel and also measure the temperature. And down here, you can see the emission spectra of the lamp, and here a superimposed picture of the emission spectra of the lamp and the absorption spectra of both the pyrimidopteridine and the pyrimidopteridine N oxides. And this overlap is indeed sufficient to promote the reaction. So looking at the excited state reduction potentials, which has to be paired with the ground state reduction potential to close the catalytic cycle. Here we're looking at a reductive quenching cycle. There we see that with the pyrimidopteridine, we are on the far right of this scale here with the excited state reduction potentials, which is awesome because we can oxidize all compounds with oxidation potentials that are below this value. And if you see the comparison here, we are very far on the right side in comparison to the photoredox catalyst. And also the ground state reduction potentials is rather high, so we have a very high span here, so which is very good to recover the catalyst because we can use mild oxidants that have reduction potentials in this area, oxidation potentials in this regime. So we applied the photoredox catalysts in some reactions. So the first one was kind of a working horse in organic photoredox catalysis, which is the decarboxylative Giese type reactions, which leads to the photomediated CC bond formation in this case. And this reaction is not new to the community. It has also been studied by other groups like Macmillan using transition metal photoredox catalysts, or also the group by König who used this Photoredox active esters and organic dyes here, or the group of Gonzalez, which managed also to decrease the base to a catalytic amount. All of these reactions usually require extended reaction times instead of this one, but in our case, we neither have a sacrificial reductant or oxidant and can also use catalytic amounts of the base. So the scope is briefly shown here. We tested a bunch of different carboxylic acids and coupled them with fumarates and maloates, or ethylidene malonates shown here. And we could obtain rather satisfactory yields. In this chemistry, usually the tertiary carboxylic acids were best because the corresponding radical is most stabilized, but we could also use secondary and in some instances primary carboxylic acids to couple, and also pharmaceutical derived carboxylic acids like shown in this section down here. So then we varied the acceptor, and we were glad that we also could use alpha beta unsaturated carbonyl compounds and achieve very high yields, or use functionalized nitriles. One limitation of this reaction is the decarboxylation of benzylic carboxylic acids, which lead to a proto-decarboxylation event. These are non-optimized conditions. In the meanwhile, we optimize this reaction and have a very wide reaction scope, and this is particularly interesting for our mechanistic studies. But concerning the decarboxylative schizotype reaction, we did some mechanistic experiments and saw that in a quenching experiment with the carboxylic acid and the persistent radical tempo, we could detect this coupling intermediate here. In deuteration experiments, we could identify that we see a deuteration in this position, which originates from, which is an intermediate carb anion. So let me quickly talk you through the catalytic cycle here. So we utilize the pyrimidopteridine N oxide as a pre-catalyst, with this deoxygenated and then excited. And this excited state catalyst is capable to oxidize the corresponding carboxylate of the carboxylic acid. So the carboxylate usually have reduced oxidation potentials by roughly 0.3 or 0.4 volts. And then these formed nucleophilic radicals can interact with microreactors to form this species here. And then the reduction potential of this radical is suitable to turn over the catalyst, to regenerate the catalyst and form this anionic species here, which then can be protonated to yield the product. So the second reaction I want to talk about today is photomediated hydroamination reaction. Also, this reaction has been studied by others, and there are mainly two reaction trajectories that apply. So either one has an amine that has a sufficiently low oxidation potential that the catalyst can oxidize this to the electrophilic ammonium radical, which then can react with an electron-rich alkene to form this adduct here. And then a hydrogen atom transfer catalyst is required to first deprotonate the amine and then perform a hydrogen atom transfer in this position to form the desired product. In another scenario, when the oxidation potential of the alkene is below the oxidation potential of the amine, the alkene can be oxidized to form this radical cation, which can then be nucleophilically attacked by a nitrogen nucleophile. Here, usually sulfonamides are utilized because they don't engage in competitive quenching of the excited state catalyst. Here's a mutual intermediate, as we've seen here. So also to convert this intermediate to the desired product, a hydrogen atom transfer catalyst is needed. And we have developed an additive-free hydroamination reaction of stilbenes with primary amines, and both compounds usually have a very high oxidation state, and only few catalysts are capable to engage these substrates into hydroamination reactions. So what we have identified is, although the oxidation potential of the amine is below the oxidation potential of the utilized stilbene, the reaction trajectory presumably goes via this oxidized alkene to form the species, and we have mechanistic evidence that our Photoredox catalyst acts as internal hydrogen atom transfer catalyst to form the desired product. So first I want to show you the reaction scope, and we tested quite a broad range of primary amines in the reaction, so linear aliphatic or branched primary, secondary, and tertiary amines can be utilized, and notably also allylic amines, as well as TBS protected amino alcohols. One highlight of this reaction is also that we can maintain the stereointegrity of an alpha chiral amine and can isolate the product as a mixture of a one-to-one mixture roughly of the two diastereomers, and you can see here that we don't see any erosion in the EE of this stereocenter in this position. So traditionally, benzylamines are not often used in hydroamination reactions because they can also form the C-centered radical in this position, which then lead to an racemization of the stereocenter, which we don't see under these conditions here. So on the side of the stilbenes, we investigated a number of unsymmetrically substituted stilbene derivatives, usually those with moderate oxidation potentials gives the best yield. So if we introduce electron withdrawing substituents, the oxidation potential increases, and this leads into a deteriorated yield. But we were really satisfied that we could also use more functionalized stilbene derivatives here, an estron-derived stilbene and tetrahydrocannabinol-derived stilbene, and very good yields. So in these reactions, we use benzylamine as a standard amine, and this can be easily protected under very mild conditions to liberate the free amine. So we've been most interested in the mechanistic aspects of this reaction, and there we applied luminescence quenching experiments. For instance, here in the upper part, you see the luminous quenching, the thermoformer plot of a solution with the excited state catalyst, which is dosed with certain amounts of stilbene. And the thermoformer plot here shows you that we have a quenching constant of roughly 65. And if we excite the solution containing the photocatalyst and add certain amounts of benzylamine, we only get a quenching constant of 33. So, but most importantly, so we see that both substrates are competent quenchers, but the stilbene is a better quencher in this reaction. And then we investigated a competitive thermoformer quenching experiment. Here you see the dosing of stilbene to a solution of the catalyst under irradiation, and you see a nice slope here. But if we add further amounts of benzylamine, it does not really quench the catalyst much more. So in contrast, if we have a solution containing the photocatalyst and benzylamine, the subsequent addition of stilbene is a very good, shows that the stilbene is a very good competitive quencher compared to the benzylamine. So, but this didn't really tell us much about, okay, I need to stop. We applied EPR experiments. Here you see a solution that is irradiated solution containing the catalyst and stilbene, and we see a 9-line EPR spectra, which shows you, which could be simulated. That's the electron coupled with 2 non-equivalent nitrogen atoms and 1 hydrogen atom, which was kind of exciting because this was an aprotic environment, and this excited state, this radical vanished immediately after the light source was switched off. And in contrast, in the protic reaction environment, we see an EPR spectra that can be simulated with a radical that couples with 2 non-equivalent nitrogen atoms and a very persistent radical. And this is a separation of the radical and the charge, and that's why this is much more persistent, because the back electron transfer is hampered. Yeah, in these on-off experiments, we then saw that in the off phase, no product formation is observed. So this hinted us that the persistent radical is not a competent species in the catalytic cycle, but rather an off-cycle species, which is shown here. And thus we concluded, because of the quenching experiments and the persistence of the radical, that the reaction proceeds by excitation of the stilbene, and yeah, then the addition here. And since we don't have a hydrogen atom transfer catalyst, but the reduction potential of this benzoic radical is too high to be reduced by the catalyst, we conclude that this species is a hydrogen atom transfer catalyst that forms the product. So let me go through. Here, this is actually, I already talked about this, so I'm very sorry about this technically issues that we had. I hope I could still convince you that the pyrimidopteridines are very exciting new organic photoredox catalysts, and in the future I'm also very excited to talk about other applications that we are working on right now. Furthermore, I'd like to thank my team, and the collaborators are highlighted in bold, and of course also the funding agencies, and you for your kind attention. Thank you very much.
Yeah, Jola, thank you very much for introducing us into this quite exciting derivative new photocatalyst, organic photocatalyst, and with really exciting and interesting photophysical properties. We have already a few questions in the chat, and let me start with one that is related to the hydroamination. So does the hydroamination also work with an alkyne? Did you try this? So with a triple bond?
Yeah, no, we did not try that. I'm also not aware. We had to check the oxidation potentials of the alkynes if this still matches.
Yeah. What about the diastereoselectivity in the case of the Michael acceptor chemistry you presented earlier in your talk?
Oh. Yeah, usually, so we don't have any stereodiscriminating factor. So this is usually an equal distribution. What you see here is often what other people also do to utilize symmetric substrates, so you don't run into this issue of a poor diastereoselectivity.
Yeah, so this was not a focus of the research, right?
No.
I would. You mentioned that when you have the amine and the alkene here in the last mechanism on there, although the amine is easier to oxidize, the olefin is the part where it's reacting. Can you give us an idea? What is your hypothesis? Well, exactly this one here. Why these 300 millivolt more kind of easier to kind of react amine is not reacting?
So this is what we investigated in the competitive transformer quenching experiments. But so if you only look at the potential, so you stop here, then you think, okay, the mechanism proceeds by oxidation of the amine, and the story is done. So we're still curious and had the feeling, like, especially because we don't see any deterioration in the EE of the stereocenter here, that something else is happening, and also concerning the substrate scope of the still bean, which was not really in line with the oxidation of the amine. And in the competitive transformer quenching experiment, you nicely see that the still bean is a much better quencher, although the oxidation potential of the benzylamine is much lower. So this, in conjunction with the longevity of the radicals, then made us conclude on
Could
the
the reason for this be a pre-assembly of that the alkene is coming in closer proximity to the photocatalyst?
Yes, this might.
Then the quenching and the electron transfer is kind of beneficial by these, or by the pre-assembly it gets just better. Could that be a reason for this?
This is possible, that we have kind of a pre-pi stacking of the still bean and the heteroarene. And what we also see is if we use these still beans, which are tilted and not planar, we have a much lower rate of this reaction, because the electron transfer is hampered, but also potentially the nucleophilic attack of the radical cation. This is formed. What we see if we, for instance, utilize secondary amines, which have a much lower oxidation potentials, the reaction does not really proceed. And what we think is that we reside in this resting state in that case.
Right. Okay. Yeah. Thanks a lot for answering all the questions and the presentation. We have to move on now. And thank you for being on the program. And I hand over to Deanne to
Thank you very much.
Great. Thank you very much, Jola, for this great talk and for the discussion. And with that, we move on to our third and final speaker for today. So our speaker is Tehshik Yoon, and to give you some brief background, he received his bachelor's degree at Harvard University in 1996, and later obtained his master's degree at the California Institute for Technology in the lab of Eric Carrera. In 2002, he earned his PhD also at Caltech, studying with David Macmillan, and went on to complete postdoctoral studies with Eric Jacobson at Harvard University. In 2005, he moved to the University of Wisconsin-Madison, where he is a professor in the Department of Chemistry. His research group is interested in the application of open-shelled reactive intermediates, such as heteroatom-centered radicals, alkene radical cations, and electronically excited organic triplets to complex molecule synthesis. Tehshik is also a co-chair of the editorial advisory board of ChemPhotoChem. And so with that, the floor is yours, Tehshik. Thank you very much for joining us today, and we're looking forward to your talk.
Great, thank you very much. And thanks to all of you who tuned in, especially those of you from Europe who are spending a little bit of your time in your evening with me. It's a great pleasure to be part of this symposium. So the chemistry that I want to tell you about is a sort of new project in my research group, or a relatively new research direction in my research group that is being led by this group of students in my group. I'll talk to you about some chemistry that was first pioneered by Nick Reed, who's now at Sanofi, a postdoc and a graduate student, Sam Gockel, and Grace Lutovsky in my group currently. So essentially, what this project comes out of is a thought process about what kinds of reactions we know how to do well using photoredox catalysis after almost 2 decades of working in this area, and what sorts of reactions still remain complicated. And one way that we can look at this is to look at the redox balance of the reactions that are typical in photoredox catalysis. When you look at these reviews of photoredox catalysis, I think that what comes out is that many of the most synthetically useful reactions that have been published over the last 2 decades in this area have been net redox neutral transformations. The first paper that Dave McMillan published in Science on this topic is essentially a photoredox asymmetric alkylation reaction. So, if you balance the reaction, this is simply a redox neutral enolate alkylation. Similarly, the reactions that have developed since then have been things like atom transfer reactions, hydrofunctionalization reactions. That was a great example of this in Jola's talk. There are also examples of trifluoromethylation reactions and even cross-coupling reactions. This has really ended up being very, very important in the field of photoredox catalysis. And I've balanced the reactions so that you can see that in general, these are net redox neutral transformations where the starting materials and the products have essentially the same oxidation states. So when you begin to think about net reductive and net oxidative reactions, it turns out that the ease of conducting these sorts of reactions differs somewhat. Photoredox reductions, these can be developed relatively easily. In fact, one of the first papers in this area was a reductive dehalogenation reaction developed by Corey Stevenson. And so these are the conditions here. It's a debromination of this complicated scaffold. This is a problem that has continued to interest the field. Here is a paper in Science a few years ago using the ConPet technology developed by our chairman, Burkhard König, that again is a photo reduction of this very difficult to reduce aryl chloride in reasonably good yields. In contrast, oxidation reactions have proven to be much more challenging to develop. And so I'm showing you here two examples from my laboratory. In fact, these are the only two examples of net oxidative transformations that my group was able to develop in the first decade of working on this problem, despite significant attempts. We found that it was relatively easy to design reactions where the terminal oxidant, in this case oxygen, is incorporated into the molecule, a so-called oxygenation reaction. But the complementary class of oxidase type reactions, where the terminal oxidant is not incorporated into the molecule, but is simply an electron sink to balance this equation, these reactions are much more difficult to develop. We did publish this reaction in a good place, but what I will tell you is that the kinetics of this reaction are poor. This reaction takes over a day. And more importantly, the scope of this reaction is very, very limited. And what we found time and time again is that as we developed reactions, we were trying to do these oxidase type reactions. We found that the scopes of the reactions were relatively narrow and the generality of the approaches was not very good. So one thing we began to think about was that when you look at these reduction reactions that seem to work quite well, the terminal reductants being used are somewhat atypical when you consider the reductants that people use in ground state thermal chemistry. Amines are inexpensive, they're commercially available, they're easily tunable, so they're great reductants, but they're not really common in ground state reduction reactions. Oxygen and peroxides are commonly used in ground state oxidation reactions. And so what we began thinking about is perhaps there's a problem in the kinds of oxidants that we were choosing to try to develop reactions around. And perhaps what we need is a similarly atypical terminal oxidant to make these reactions work. So of course, we're not the only people who have been working in this area. And so, it's not the case that people in this field have not been able to develop oxidase type reactions. I'm showing you several examples here of reactions that are really quite useful that use terminal oxidants like oxygen or peroxides to develop really useful reactions. But what I would say is, again, there are some really interesting limitations in scope and generality that come out of these experiments if you look at them a little closely. The reactions that seem to have broader scope and broader generality are those that use these somewhat untypical oxidants, things like nitroarenes or like perhalomethanes that, I think are not commonly used in ground state chemistry, but they seem to work really well in photoredox catalysis. The downside is that when you think about how practical these are in real industrial scales, of course, perhalomethanes are greenhouse gases. I think nitroarenes have some obvious waste stream problems associated with them. And so we began to think about, perhaps there is a way of trying to design reactions that would use different kinds of terminal oxidants. Okay, let me focus in on this experiment just to give you a sense of what we mean by the scopes being limited in surprising ways. So this reaction is, I would argue, one of the sort of seminal contributions in organic photoredox catalysis by Dave Nisevich, published in Science several years ago. The way this works is this strongly oxidizing acridinium photocatalyst oxidizes an arene to the corresponding radical cation. This radical cation traps a nucleophilic nitrogen to make a delocalized pentadienyl radical. TEMPO oxidizes that radical to re-aromatize, and then the TEMPO is turned over by using oxygen, molecular oxygen, to regenerate the TEMPO co-catalyst. This works really quite well. It's a beautiful transformation. The limitation in scope that Nisevich notices, and I say this not to pick on Dave, but rather because he does a really good job of characterizing what the byproducts are. This arene also oxidizes within the range of the strongly oxidizing photocatalyst. It traps the nucleophile just well and does give you some of this product. But the remainder of the mass are oxidized byproducts such as this one. And where this comes from is the fact that one of the things you can do from an arene radical cation is that you can deprotonate at the benzylic position. The benzylic radical then reacts at diffusion-controlled rates with the open-shelled triplet dioxygen to make a hydroproxy radical that's very reactive and decomposes to give these kinds of products. In addition, whenever you have an excited state, a triplet excited state molecule, one of the ways it gets quenched is to react with oxygen at diffusion-controlled rates, either to make singlet oxygen or superoxide, both of which are also very, very reactive oxidants that can react with electron-rich oxidants. And so whatever the mechanism is, the terminal oxidant has various mechanisms by which it can react with this substrate to give undesired oxidation products of relatively unreactive compounds, functional groups such as benzylic CH bonds. So we began thinking about how we might be able to design similar sorts of reactions that would perform net oxidative transformations, but use terminal oxidants that were atypical in ground state reactions, were relatively inexpensive and environmentally innocuous, and would also be able to tolerate photoredox conditions without generating these very reactive, open-shelled, oxygen-centered radical intermediates that could decompose, especially electron-rich substrates. So again, our starting point was a reaction that had been studied by Nisevich, these hydrofunctionalization reactions that are catalyzed by these acridinium salts. The way these work are by photoredox oxidation of an alkene to make an alkene radical cation. These are electrophilic in the same way that the arene radical cation is. Trapping of the nucleophilic nitrogen gives you a benzylic radical. And then Nisevich's really key insight was that you could generate the product of hydroamination by reacting this benzylic radical with a hydrogen atom donor. So it couples a 1 electron oxidation step as the activation step, followed by a 1 electron reduction as the termination step. So the oxidation and the reduction balance out to give you a redox neutral hydroamination. And so what we began to wonder is whether or not, instead of terminating the process with a 1 electron reductant, could we replace it with a 1 electron oxidant, giving us carbocationic reactivity that could trap the other nucleophile and give us the products of a net oxidative reaction, in this case, an oxyamination reaction. So after a bit of optimization, we were able to find these conditions using a slightly different photocatalyst, this beryllium photocatalyst. And importantly, the best terminal oxidant we were able to find is a copper-2 salt, copper TFA. Many other copper salts give us some yield, but the TFA counterion seems to be the one that's ideal for this particular application, showing you how you can tune the identity of the copper catalyst. But importantly, in the process of developing these conditions, we tried many, many other oxidants. Some of them didn't give us any product at all, were essentially incompatible with these conditions and didn't give us oxidation chemistry, so we saw no conversion of the starting materials. But the ones that included oxygen or would otherwise generate oxygen-centered radicals after 1 electron reduction, these are completely incompatible with the electron-rich starting materials, and all we saw was complete decomposition of the starting materials without any formation of the desired oxyamination products. The scope of this reaction is relatively broad, but really the scope was not the point of this, but I did want to highlight the fact that we can tolerate a variety of different kinds of groups on the alkene that we're oxidizing. They can both be intermolecular reactions as well as in some cases intramolecular reactions as well as in some cases intermolecular reactions simply using carbamate. And because these are simply 2 nucleophilic attacks of 2 different heteroatoms on various electrophilic species, we can do not only oxyaminations but also diaminations and dioxygenation reactions as well. So mechanistically, what we think is going on is that the first step of this reaction is exactly what Dave Nisevich has developed. Photooxidation of an electron-rich alkene generates an alkene radical cation that traps the nucleophilic nitrogen to give us this benzylic radical. So all of that is Nisevich chemistry. We think that what copper is doing is J. König chemistry from the 1960s and 1970s. König had shown that electron-rich radicals react with copper-2 oxidants at diffusion-controlled rates to generate either a carbocation or a copper-3 alkyl that acts essentially like a carbocation. This can trap the oxygen of the tert-butyl carbamate. The tert-butyl group leaves and gives you the final products of the oxyamination. So what we've done is we've coupled Photoredox catalysis with some really old J. König oxidation chemistry. And I guess in retrospect, we should have known that this was possible for two reasons. J. König had shown us that these radicals get oxidized by copper-2 salts very efficiently under a variety of conditions, just regardless of how you generate these radicals, either using chemical oxidants or electrochemically or other sort of thermal fragmentation reactions. So there are a variety of ways in which this copper salt works, regardless of how the radical is generated. Moreover, by the time that we began these studies, there were several examples that were pioneered by Melanie Sanford, but then followed up in a lot of detail by Dave McMillan, of the use of copper catalysts along with Photoredox catalysis. So we know that copper salts cycling between copper 1 and copper 2 are easily compatible with these photoredox conditions. And so the idea of them being catalysts and being tolerated by Photoredox catalysis also seems to indicate that they should also be amenable to being used as terminal oxidants in a stoichiometric sense using Photoredox catalysis. So the challenge that we had when we began trying to publish in this area, trying to make the case for copper salts being practical oxidants, is that there is a certain kind of sense that the use of stoichiometric metals in chemistry is to be avoided. And I think that's true in general, but of course you need a terminal oxidant for a net oxidation reaction, and you need for that to be stoichiometric. And when you compare copper salts to a variety of other oxidants that are very commonly used in organic oxidation reactions, first of all, copper salts are in general easier to purify than the organic byproducts of these oxidation reactions. So it's a simple filtration through silica rather than a tedious chromatography. The byproducts of copper salts are environmentally more benign than the aromatic byproducts of many of these terminal oxidants. Perhaps most importantly, however, the cost of these copper oxidants is at least an order of magnitude cheaper than the majority of these oxidants, with the exception of the copper TFA salt that's optimal for the chemistry that I just showed you. I don't really understand why it's so expensive, but what I can tell you is that you can synthesize it very easily in one step simply by mixing copper carbonate with TFA. Both of these are commodity chemicals, so really this ought to be the same cost as the rest of these copper salts. And in fact, this is how we do it. The quality of the copper TFA that we synthesize is actually a bit better than what we buy from Pospech. So the cost of the copper oxidants is also not problematic. So I would argue that these are economical, relatively non-toxic terminal oxidants that are practical, atypical oxidants for Photoredox catalysis. So we've been showing that this is amenable to a variety of other reactions. Here is a benzylic oxidation reaction that we published a year ago. The way this reaction works is very similar. In this case, this iridium photocatalyst oxidizes the arene to the corresponding arene radical cation. This is the deprotonation reaction I told you about before to generate this nucleophilic benzylic radical. The König chemistry doesn't care how you generate the radical. Copper-2 reacts with the electron-rich radical at diffusion-controlled rates to make either a carbocation or a copper-3 alkyl that behaves the same way. And then oxidative coupling with an oxygen nucleophile gives us the product of this cross-coupling reaction. The scope of this reaction is broad. It doesn't care about the sterics or the functionality of the oxygen or the acid. With respect to the benzylic CH bond donor, it seems like we do need to have an alkoxy group of some kind in either the para position or in the ortho position to give us good yields, but that also gives us really good selectivities that are kind of interesting. For instance, we can tolerate CH bonds that are about as weak as the benzylic CH bond here and still get selective oxidation of the one that would lead to the carbocation that is essentially a quinone methide carbocation, a highly stabilized carbocation from this electron donating group. We can also tolerate things like primary alcohols amines or sulfonamides, even B-pin groups. So the functional group compatibility of this method is really quite broad. So the combination of the high site selectivity and the functional group compatibility got us thinking that this is a good way to modify complicated pharmaceutical compounds. So we bought essentially every compound that we could find that has a benzylic CH bond on an electron-rich aromatic ring, and we showed that we could functionalize these compounds using not only just simple alcohols, but also use this as a way of doing cross-coupling reactions between these drug molecules and amino acids, protected sugars of various sorts, and natural products as well. So it's a really interesting way of kind of coupling these complex flat fragments together. The downside of all of this is that we always seem to need this electron donating alkoxy group on the arene to make this reaction work. If we don't have this electron donating group, then essentially what we have is no reaction whatsoever. And when you think about why that, about the electronics of this key photoinitiation step, this makes a lot of sense. The oxidation potential of this ethyl anisole is about 1.5 volts versus SCE. So the methoxy group has a real impact on the oxidation potential. If we delete that methoxy group, the oxidation potential is almost a volt more positive. So this is outside of the range of everything except for the most oxidizing photocatalysts. And so the more oxidizing potential we have in the photocatalyst, the less we can tolerate the sort of functional groups that sort of make this method, we think, really useful. And so a thought that we had was that perhaps instead of oxidizing the arene, we could install a functional group that is more easily oxidized and then can be removed to give us the same radical. So we thought about using carboxylates that are even easier to oxidize than these electron-rich arenes. Decarboxylation would give us the same benzylic radical that could still intercept copper-2 salts and get oxidized in the same way that Jacob G. taught us about in the 1960s. So the question was whether or not we could do a decarboxylative coupling reaction. And the answer is yes, we can. Copper triflate in this case is the best terminal oxidant. Again, it's a cross-coupling reaction using one equivalent of the carboxylic acid and essentially one equivalent of the nucleophilic coupling partner. We began by using sulfonamides simply because sulfonamides were of interest to these collaborators that we had at Pfizer. And so we had this reaction working really well in very good yields. But what we found pretty late, unfortunately, was in a control experiment that it turns out we don't need a photocatalyst. This reaction works just as well with a photocatalyst and without a photocatalyst in essentially the same yields. So that was a surprise. And so we looked at the scope of the reaction under these conditions. We found that, certainly the electron, the identity of the sulfonamide doesn't matter, but certainly more electron-rich carboxylic acids do work better, but we can get down to even some relatively electron-deficient carboxylic acids and still get good yields of the coupling. So functionality doesn't matter. We can change the identity of the sulfonamide group. We can use primary, secondary, tertiary carboxylic acids. Aliphatic tertiary carboxylic acids decarboxylate, but it turns out that the carbocation or the copper-3 alkyl undergoes competitive elimination to an alkene. If we use a constrained tertiary carboxylic acid that cannot eliminate, then the coupling works just fine, but this is still a limitation of the current scope of this reaction. With respect to the nucleophile, in addition to sulfonamides, we can use things like carbamates, both cyclic and acyclic. We can use amides. We can do some carbon-carbon bond forming reactions. So here are examples of Friedel-Crafts reactions. And we can also, under slightly different conditions, make carbon-oxygen bonds, in this case with a sugar, in this case with a simple alcohol. And again, we've got this combination of really good functional group compatibility, and in this case, perfect site selectivity, because the site of the oxidative coupling is exclusively at the carboxylic acid. So we can also modify real drug molecules. These are nonsteroidal anti-inflammatories of various sorts that we've functionalized with different kinds of sulfonamides. In these cases, we're using complicated sulfa drugs, and in this case, Celebrex itself, in really good yields, again, using a one-to-one stoichiometry of the two coupling partners. So I think this is a really interesting oxidative coupling reaction where we're taking two nucleophilic partners and bringing them together using the copper salt not only as a terminal oxidant, but probably also as a photocatalyst of some sort. Everything we put into this pot has no color to it, right? So this is a non-colored molecule, this is a non-colored molecule, and the copper salt only becomes strongly colored when we put everything together in the same reaction vessel. So presumably what we're making is some sort of complex of a copper carboxylate salt that is photoactive, that absorbs the light and initiates the reaction. The question was exactly what this sort of species looks like. So here's the general idea of what we thought was going on. We're self-assembling some kind of copper carboxylate. I'm just sort of drawing some general formula for what that might be here. You irradiate it. And so what we thought might be happening is essentially a homolysis of this bond. In proper physical terms, what we think this is a ligand to metal charge transfer, but an organic chemist can simply think about it as a homolysis of that bond with one electron going this way and one electron going that way to make copper 1 salt. The carboxylate leaving group in this case would be a carboxy radical. These carboxy radicals can undergo fast decarboxylation. Many examples of this process are known in the literature at this point. And again, the copper 2 salt will react with this radical, no matter how it's generated, oxidize it, and do a coupling reaction with the nucleophilic reaction partner to give us the products of this nucleophilic coupling. So the question that we still don't have a great answer for yet is, what is the nature? Sorry, forgot to say, there is actually some precedent for this kind of process in the physical literature. And there are actually many examples of it, but we thought the most direct was this example from JPhysChem. It is the decomposition of this copper 2 malonic acid complex. Irradiation gives you this MLCT excited state that I like to think about as a homolysis of the copper oxygen bond. Decarboxylation followed by copper-mediated oxidative coupling gives us this glycolic acid. And so this process does seem to be precedent in the literature. It just hasn't been used in synthesis very significantly as far as we can tell. So again, the question is, what is the nature of the copper photoactive species that's involved here? What I can tell you right now, it is that it is not the typical paddle wheel-shaped copper acetate type dimer. Because we can synthesize this complex, we can characterize it crystallographically, we know what we have here. But if we take this and we irradiate it under the reaction conditions, we see absolutely no products arising from this oxidative coupling reaction. So we don't think this is the active photocatalytic species. Instead, what we think is going on is we're generating some metastable copper carboxylate monomer, whether it's this monomer or that monomer, we don't really know. But in any case, this must be the species that both initiates the photoreaction as well as the oxidative coupling reaction. So to investigate this, Sam did a really interesting titration study where he began with copper triflate all by itself. And I said copper triflate by itself essentially has no strong absorption features in the visible regime where we're irradiating. As he begins to titrate in more and more of the carboxylic acid, you see first a feature growing in here with a lambda max of about 304 nanometers. That plateaus somewhere around a 1-to-1 stoichiometry of the carboxylic acid to the copper 2 salt. As we begin to add more than one equivalent of the carboxylic acid, this feature begins to decay, and instead we see a new feature growing here with a lambda max of about 260. This is the typical lambda max for copper acetate dimer, the paddle wheel dimer, and in fact is also the lambda max for the authentic copper paddle wheel dimer that we were able to synthesize that I showed in the previous slide. So what we think is going on here, and you can kind of see from a plot of, let's look just at the shoulder at about 350 nanometers here. You can see that it grows in, maximizes at about a 1-to-1 stoichiometry, and then begins to decay. And about this point, this new feature at about 250 nanometers begins to grow in, and then maximizes at about a 2-to-1 stoichiometry. So we think again that this higher energy feature is the unproductive dimer. And the photochemistry is being mediated by this metastable monomeric species, and it seems consistent with many of the copper 1 carboxylate monomers we're able to find in the literature. And we're radiating on this shoulder that extends out into the visible regime. And so we're activating this compound that generates the carboxylic acid, the carboxy radical via this LMCT activation, and then decarboxylation followed by copper oxidation gives us the products of these copper oxidation reactions. So we're really excited by this. I think that what we take away from this essentially is that our early attempts, at least in my group, to develop net oxidase type photochemical transformations was really limited by the fact that we were choosing the wrong oxidates. based on the fact that as synthetic organic chemists trained on ground state chemistry, that we reached for terminal oxidants that are sort of difficult to use in a productive way in photoredox catalysis. And so we think that the best terminal oxidants in photoredox catalysis are different from those that would be utilized in ground state chemistry. And I told you about the use of copper-2 salts, which we think are practical, inexpensive, and relatively innocuous. And when you look at the amount of metal that can be a trace impurity in pharmaceutical compounds, copper is in the same category as lithium, which is to say not innocuous, but if you're willing to use stoichiometric LDA or butyllithium, stoichiometric copper is about of the same problematic magnitude. And we think they work well basically because they tolerate one electron oxidation state changes from copper-2 to copper-1 to copper-0 without generating reactive oxygen species such as oxygen radicals, singlet oxygen, and superoxide that could really be problematic when you're trying to functionalize complicated electron-rich molecules. And finally, what I finished up with is the fact that since we are using transition metals as terminal oxidants, there's a rich photochemistry of first row transition metal coordination complexes. And I think there's already some beautiful papers that are being published right now. And so I think there are a lot of great applications that could come from the use of copper-2 salts, not only as terminal oxidants, but also as the photocatalysts that get these reactions working as well without the need for other photocatalysts at all. So let me finish there and thank first the organizers for putting together this great symposium and giving me the opportunity to close a great day of chemistry. Let me also thank my group. This is our most recent group photo. About half the group is now working on this copper chemistry in one way or another. These are my current collaborators. I especially want to point out that a lot of this copper chemistry came out of collaborations funded by Pfizer and the American Chemical Society's Green Chemistry Initiative. They were interested in the fact that base metals were useful terminal oxidants in this sort of chemistry. So let me thank them. Once again, let me thank you, and I'm happy to answer any questions about this chemistry.
Yeah, Tehshik, thank you very much for this very nice story. I think it's really developed nice to show us what kind of oxidative photochemistry, where the challenge is and where your solutions are. I think this was very convincing. So there's time for questions in a way. I don't see one now here, but please ask your questions as before in the chat. Let me start with a question. I think it's very obvious. Looking at the chemistry you showed there at the end, you don't know exactly what a copper species is. You have a good idea. What about making these last transformation enhancer selective?
Yeah,
I think that's a great obvious because there's copper chemistry around where you have chiral ligands. I'm sure you tried.
We have. We have, but we've only tried certain experiments. So essentially the problem here is that we're using stoichiometric copper complexes. And so in the experiments we tried has required stoichiometric chiral ligands. And so we've certainly tried, we have not seen anything yet in the experiments that we've tried. And so I think that the cost of these asymmetric methods is prohibitive. So what we would really like to do is to understand this chemistry a little bit better. What I've pointed out incidentally is that I've drawn some acetonitrile ligands, and you'll see the conditions here. There's acetonitrile added. We began and we discovered this reaction initially in acetonitrile, and we found ultimately that a better solvent was a more non-polar solvent, but we still needed acetonitrile. The acetonitrile seems to have some very minor impact on the UV-vis spectrum, so we're reasonably confident that the acetonitrile is a ligand in this case. And there are some really subtle ligand effects that we're observing. So for instance, I mentioned that the conditions to make carbon-oxygen bonds are slightly different. The major difference here is that instead of using an inorganic base, we use an organic base. We use pyridine. When we add pyridine to this copper salt, we see a significant redshift in the absorption of the spectrum. It's visibly a much deeper color than these conditions without the pyridine base. So it's very clear that the ligand has an impact not only on the chemistry, but also on the photophysics of whatever copper species we're generating. And so I'm really interested in this. I would really love to figure out exactly the nature of these ligand effects so that we might be able to use that to use perhaps either a catalytic copper complex or more importantly, just catalytic ligand to see if we can get to using asymmetric ligands for enantioselective coupling reactions of this sort.
Yeah. So the oxidation of copper 1 back to copper 2 is a very easy oxidation to do. So did you consider to use kind of recycling systems?
Yeah, we did, right? So let me show you these conditions here. Essentially what's happening here is we're using catalytic photocatalyst, but we need, of course, stoichiometric oxidant in a stoichiometric oxidation reaction. So if we wanted to use a catalytic copper, rather than having the copper regenerate the photocatalyst here by this second oxidation step, what we would need is another terminal oxidant to turn over the copper. So we tried. And there's a Beilstein Journal of Organic Chemistry paper where we sort of report these results. It was not particularly successful. We tried all of the other terminal oxidants that we typically screen in ground state chemistry, and we had the same problems. Things that would generate oxygen-centered radicals or superoxide or singlet oxygen, those gave us complete decomposition. The only terminal oxidant that we could find that would turn over copper 1 salts productively were silver 1 salts, right? And so certainly do it, but silver is more expensive, it's more toxic, hard to purify. So ultimately, we couldn't convince ourselves that there was any reason to turn copper is such a good terminal oxidant, a practical terminal oxidant, that the bar for finding something to turn it over was much more complicated. So we're still thinking about it, working on it, but we don't have a good solution.
Right, okay. Let me close with a more kind of conceptual question. You showed us at the beginning how you kind of sorted out this question and you came to the oxidative reactions on there. And I fully agree with you with all the arguments you gave on there. But when we look from the energetics, the advantage of photocatalysis is, of course, we bring in energy in the system to overcome activation barriers. So at milder conditions, that is one thing. But the real benefit of photocatalysis would be a kind of reductive reaction, so either redox neutral reactions or reactions where we at the end store some energy in the molecules. An oxidation, a net oxidative reaction is typically exothermic from the thermodynamic grounds. So my provocative question would be, would it be more better to look at kind of ground state catalysis to do this? So do we really use the benefit of light excitation when we do oxidation reactions?
I think that's a great question. You're right that one of the real benefits of photochemistry in general is the possibility of doing formally endergonic chemistry, where the energy of the photon counteracts the unfavorable thermodynamics of an uphill reaction. And there are many examples of this that I think are absolutely beautiful. And you're right that in oxidation reactions, many of them are combustion reactions. They're downhill. I actually haven't worked out the thermodynamics of these processes, but you know, I think that it's very reasonable that these are downhill reactions. I guess there are other benefits of photoredox chemistry other than doing uphill reactions. And one of them is, of course, that what we've learned over the last decade and a half of photoredox catalysis is that photoredox catalysis is a beautiful way of making open-shelled radical intermediates and accessing that chemistry under very practical conditions. And so we've shown that we can use those radical intermediates that are generated from many, many different sources using many different strategies in lots of different powerful reactions. And we've used those in net reductive reactions and in net redox neutral reactions. The ability to use them in oxidation reactions, I think, is important because when we think about the overall flow of chemicals from petrochemicals to drug molecules or other functionalized molecules, it's the functional groups that make them functional. And so the oxidation reactions are synthetically important because these are the ones that introduce those polar functional groups. So yeah, I agree. I think there are many reasons to be interested in these things. You know, the reason that we were so interested in oxidation reactions is for this last reason, because I think that for the purposes of the communities that use these chemistry, I think our inability to do the oxidation reactions really was a gap that was worth addressing.
Fully agree. No, I think it's indeed great chemistry and definitely important to pursue this, because the classic photochemical oxidation via singlet oxygen, they are simply not selective and not really useful in synthetic chemistry. And this here is definitely very useful and a big step in the direction of selective photochemical oxidation chemistry. Tehshik, thank you very much for being part of the symposium. I think we learned a lot. I also have to thank all the other speakers. It was, I think, a great afternoon with great chemistry here. Thank you for joining. I think it's a great way kind of to share new findings and thoughts in photocatalysis. I hand back to Anne for closing our symposium for today and say bye-bye, see you next time.
Yeah, thank you very much, Burkhard. Yeah, I can only second what you said. This was a great event, and thank you for moderating this, and especially also to our speakers, so to Timothy, Jola, and Tehshik for presenting their research here today and for giving these fantastic talks. And lastly, of course, to our viewers, I think we had up to 500 people watching here, which is a great turnout, and everyone also asked lots of questions, and it was a very lively scientific discussion, so that's great. And I'm also happy to let you know that we have one final event coming up this year, and for this I will quickly share my screen and show you the following following slide. So we are, I think now it's correct. Okay, so it's the virtual edition of the Young Investigator Workshop, which is hosted in collaboration with the Organic Division of EuChems. And here we have 3 afternoon sessions full of organic chemistry, and these young investigators will present their research in very short talks, so in 15-minute talks, and Photoredox Catalysis is also among the topics covered, and we have a great lineup of these young investigators, for example, Luca Dell'Amicchio, Daniele Leonori, Elaine O'Reilly, Song Bim, and many, many more. So please check out this event. The registration is already open, and you can find more details on our Twitter page and also on the EuChems homepage, and I will quickly post the link here in the chat. And so please join us for this next, our last and final event of the year. With that said, Deanne and I would like to close the event. So thank you for joining, and hope to see you soon. Bye.